Okay, so what if I told you the future of solar power? Well, it isn't on land. It's on water. Yeah, you heard that right. Today, we're diving deep into the world of floating solar. We're going to explore some incredibly innovative designs that are turning lakes, reservoirs, and even the open ocean into this brand new frontier for clean energy.
It's a fair question, isn't it? I mean, it sounds a little out there, I get it. But as we're about to see, putting solar panels on water isn't some gimmick. It's actually a pretty brilliant solution to some of solar energy's biggest challenges.
And the benefits are? Well, they're pretty amazing. First off, it saves valuable land that we can use for other stuff, like farming or housing. Second, and this is a huge one, the water acts like a natural air conditioner. See, solar panels, just like your phone, lose efficiency when they get too hot. Being on the water can boost their output by an incredible 5 to 15%. And with no buildings or trees casting shadows, it's just a win-win-win. So now that we know why we're doing this, let's get into the nitty-gritty of how it all actually works. Okay, let's dive in. Floating photovoltaic, or FPV for short, is exactly what it sounds like. Solar panel systems mounted on structures that float. And yeah, this whole thing got its start on calm, freshwater lakes, but the real prize, the new frontier everyone's chasing, that's the huge and incredibly challenging open ocean. This slide right here gives us a great roadmap for our journey today. Basically, all these FPV designs fall into one of two main families. You can think of it as two different philosophies for dealing with the water. The first, pontoon type, is all about building a platform to stay above the water. The second, superficial, is about designing panels that can live right on the water surface. So let's start with the pontoons.
Right, so the pontoon approach. This is the most common and established method out there. The core idea is really simple and intuitive. You build a stable raft, and then you mount standard solar panels right on top. It keeps them safe, dry, and up and away from the water.
And Class 1 is, the OG, the original design. This is where it all started. Just picture a classic raft. Long, parallel plastic floats, kind of like cylinders, connected by a rigid metal frame. The solar panels then get mounted securely right on top. It's a simple, robust, and proven concept.
So the big strength of this design is how versatile it is. It's sturdy, and you can easily add trackers that let the panels follow the sun, which squeezes out every last drop of energy. The downside? Well, it's expensive, and its rigid nature is also its biggest weakness in rough seas. Because it tries to fight the wave's energy instead of moving with it, the whole structure is under just immense stress. Most of these Class 1 designs can only handle waves up to about 2 meters, and that's just not going to cut it for the open ocean.
Now, the next evolution was Class 2, which took this brilliant modular approach. Instead of one giant raft, what if each solar panel got its own individual float? Then you just connect them all together, kind of like Legos, to form a massive array. This one simple idea completely changed the economics of FEP. The big pro here is cost. By getting rid of that expensive metal support frame, Class 2 designs became way cheaper, which led to their explosion in popularity on calm lakes and reservoirs. But, and this is a big but, this design was built for cost savings, not for strength. The very thing that makes it cheap, that lack of a unifying frame, also makes it vulnerable. It can only handle small waves, up to about 1 meter high, making it totally unsuitable for the harsh marine environment.
And this next one shows a real move towards ultimate stability. Class 3 designs are basically massive, continuous floating islands. You build one giant, incredibly stable platform, and then you can literally just walk around and install the solar panels almost as if you were on solid ground.
The advantage here is crystal clear: unparalleled stability and safety. That makes maintenance so much easier. This design is highly suitable for the sea. In fact, one project out in the North Sea has already survived mind-boggling 10-meter waves. The trade-off, as you can probably guess, is the cost. The sheer amount of material and engineering needed to build a seaworthy floating island makes this the most expensive of the pontoon options.
Okay, so we've looked at the pontoon-type designs, the ones that try to stay above the waves. Now let's explore that other family of PVA, the superficial designs. Instead of building a raft to stay above the water, this approach fully embraces it. It's a lot like a lily pad. So why would you put panels directly on the water? Well, you get the absolute best cooling effect, which means maximum efficiency. With a lower profile, they're way less affected by wind. The natural movement of water and rain helps wash off dust, and they have a much lower visual impact. But this design introduces a huge new challenge. The panels are now directly and constantly exposed to the full raw force of the waves. So there are two really fascinating ways engineers are dealing with that challenge. The first is the rigid or submersible approach. And get this design is a platform that can actively sink itself. When it detects moderate waves coming, it can submerge down about 2 meters below the surface, letting all that destructive wave energy pass harmlessly right over the top.
It's a brilliant idea, right? Instead of fighting the waves, you just get out of the way. The problem is, its offshore reliability is still a big question mark. Any complex mechanical system has more points of failure, especially when you throw corrosive saltwater into the mix. And for the truly massive waves of the open ocean, sinking just 2 meters often isn't deep enough to escape their power.
The second strategy is the flexible approach. This is the go-with-the-flow design. Instead of avoiding the waves, this design just rides them. It uses either naturally flexible thin-film solar cells or standard panels mounted on a thin, flexible membrane that simply moves and undulates with the surface of the water.
The benefits for offshore use are huge here. You get to eliminate all those heavy, expensive support structures, which makes it much lighter. And that also means you need a less robust and therefore cheaper mooring system to hold it in place. Now, the crucial point here is that this design trades some efficiency for resilience. Because the panels lie flat, you can't tilt them towards the sun for that perfect energy capture. But in return, you get a system that can gracefully handle very, very rough seas. Okay, so we've just walked through 5 distinct design philosophies. Each one has its own brilliant ideas and its own unique trade-offs. Now let's put them all side by side to see how they really stack up. So the ultimate question really is, which of these concepts is best suited to truly conquer the powerful, unpredictable, and frankly kind of scary environment of the open ocean? This table lays it all out beautifully. If you look at that marine suitability column, you really see the story. Class 2, the cheap modular design, yeah, rated low. Class 1 is moderate, kind of middle of the road. But Class 3, the floating island, and the flexible design, they both score high. Now look at the relative cost column. Class 3 has high suitability, but it also has the highest cost. The flexible design, however, combines that high marine suitability with a much lower cost, which makes it a very, very compelling option for the future. You can see each one has its own key feature, from the robust raft of Class 1 to the wave riding of the flexible membrane.
Which brings us right to our final thought. We now have proven designs that can survive 10-meter storm waves in some of the world's roughest seas. As this technology matures and costs keep falling, it's pretty clear that we are at the beginning of a whole new era, where vast floating solar farms could become a major pillar of our global energy supply. The future of solar power is here, and folks, it's floating.